Welcome back with another lecture from organic chemistry. In this lecture, I'm going to go through a hydroboration oxidation reaction. And this reaction is similar to acid catalyzed hydration. The only difference between them in acid catalyzed hydration, the OH was added to carbon with more substituent. And we called it Markovnikov's regioselectivity. And in this case, the OH will be added to a carbon with less substituent. And that's the reason I'm going to call it anti-Markovnikov's regioselectivity. And so there is a regioselectivity, there is a preference here, and the preference here is, or we can say the reaction is in favor of carbon with less substituent, okay? Less substituent. The output, we will have OH attached to carbon with less substituent and hydrogen to carbon with more substituent. Okay, and when we add H and OH to like a double bond, addition is going to be from one side, okay, either from the top or the bottom. It's not like one up, one down. That's not going to happen. Addition is happening on one side of the molecule, and because it's happening on one side, we call it syn addition. Okay, it's a syn addition. A syn addition, whenever the addition of two groups that they are coming to the double bond, they are going to add it to one side of that double bond. And in this case, we say there is a stereoselectivity. What does it mean? It means a reaction is going to prefer only reaction is going to happen only on one side. Okay, on one side, either up or down, not both of them at the same time. So stereoselectivity means when the reaction is happening on one side. Okay, one side of the technically the double bond. The same time is going to happen either on the top or at the bottom of it. We will go through stereoselectivity with more details. And let me practice some example. Okay, so in this case, we have a double bond, and there is a methyl also attached to the double bond. We can have H and OH to be added to the double bond. Okay, where we're going to add the H it will be added to a carbon with more substituent. Okay, and the question is going to be which carbon? Okay, we have a carbon. This carbon is a tertiary carbon, and here is a secondary. Remember, this carbon is already has one H, so there is one H there already. Okay, and now when you add the two groups, you will add them from one side. So either up or down. Okay, up or down. Let's add them to the top of the molecule. If I add both of them to the top, so I will have one substituent here, top, another one there. Both of them are up. Okay, and this is gonna be it will be the H. Okay, why this one is gonna be the H? Because we have a methyl. And where is the methyl? Methyl is going to be back. This is the methyl. Okay, I'm talking about this methyl. Okay, so that's the methyl. Okay, and if H is there, then that means OH is going to be here. And back of this molecule, we're going to have H. Okay, that's the original H that was attached to the molecule. Okay, so the addition happened through syn addition and happen through on the top of the molecule. So this one, I will say from up top of the molecule, and it's a syn addition. Okay, let's do it from the bottom of the molecule. In that case, both those substituents, they will be added to back. This is going to be OH, and H it will be here. Where is going to be the methyl group? The methyl group, it will be in this position. That's going to be the methyl, and here we will have the hydrogen. Okay, so this is CH3. Okay, this is CH3, and that's going to be the hydrogen. Okay, OH and H, now they are back of the molecule. These two are back. That one also back. So addition happened to one side of the molecule. Okay, and now let's assign the configuration. The configuration for the first carbon, the one that it has OH, it will be R configuration. S configuration, because it's a counterclockwise. And next one is going to be, let's say, 1, 2, 3. That's going to be R because hydrogen facing to us. It will be S. So this one, it will be S. We got S and S. Again, let's double check it. Okay, so I have 1, 2, 3. Okay, it will be SS. Okay, and here we have OH. It's going to be 1, 2, 3. It's supposed to be S, and I turn to R. Okay, here we have 1, 2, 3. This one, it will be R. Okay, so these two are enantiomer. Okay, we got two products, and these two products are non-enantiomers. we have a boron that attached to 3 hydrogens. Boron is not active. That means it has an empty orbital, similar to carbocation. Carbocation, you have a carbon with an empty orbital. And we say carbon is not stable because it's not active. Okay, so that empty orbital, it can get involved in, we can say, nucleophilic attack. Okay, and I want to talk about that one. Okay, why the reaction is happening from one side of the molecule, either from the top or the bottom of the molecule, and it's not happening from up and down. And I want to understand that part of it. Okay, so here, electronegativity of hydrogen is 2.2, while electronegativity of boron is 2.04. So when you attach these two, hydrogen is going to pull to itself. Hydrogen, it will have negative charge. Okay, be careful. This time, hydrogen will have negative charge. Any of this hydrogen, it has a negative charge. So when hydrogen leaves the system, hydrogen will leave the system as hydride. Okay, hydride. That means it's going to have a negative charge. It will be H-1. Okay, that's one. And next thing is, boron is not active. It has empty orbital, and this empty orbital, it will be a p orbital. Okay, the plus minus. Okay, it's an empty orbital. Okay, p empty orbital. Okay. Now let's look to the alkene. Alkene, you have carbon. Okay, you have a carbon. Sorry, you have 2 carbons. Okay, one of them, it has 2 hydrogen. Let me show those 2 hydrogen. 2 hydrogens here, and the second one, it has 2 methyl groups. This one is a tertiary carbon, while this one is a primary carbon. Okay. Now, is there any chance to have a resonance structures? Yes, it's possible. Okay, and let me show them. What if this double bond for a second, this double bond break? Okay. Question is, where do you want to move those electrons? I'm going to say the tertiary is going to be more stable than the primary. So how about this? Let's take those 2 electrons and move them to this carbon. Okay. If we move them there, then this carbon is going to have a lone pair. Okay. This carbon is going to have a lone pair. So I have a carbon with a lone pair. How about the second carbon? This carbon, okay, the one at the bottom, is going to have a positive charge. So now that this one, it has a positive charge. Okay. Now, okay. Now what will happen? Okay, here. Now we have a carbon. Okay, carbon that it has. Okay, and the carbon that it has a negative charge, and one of them it has a positive charge. Okay, we're here. The carbon with a negative charge, it can find boron. Okay, it can find boron. Boron, it has empty orbital, and this is the empty orbital of boron. Okay, very soon it will share electron with that empty orbital. Okay, while it's establishing bond with boron, okay, the carbon that has empty orbital, and that empty orbital is here. Okay, this empty orbital in this direction. Okay, it will have interaction with the hydride. So this hydrogen is going to take these 2 electrons, and it will put them technically inside the carbon empty orbital. While the carbon with the lone pair, it will share them and put them inside the empty orbital of boron. So what do we get? We get this. We get carbon. This carbon, it will be attached to boron, while that carbon, the one at the bottom, will be attached to hydrogen. And of course, that hydrogen is attached to boron. And here we have 2 hydrogens, while the carbon bottom, that one, it has the 2 carbons attached to it. Okay. Now, as you see, the addition of boron and hydrogen is happening, okay, to one side of the molecule. Okay, at the same time, both of them, they got added, and that's the reason we say this is a scene addition. Okay, scene addition. And why is a scene addition? Because again, this is, like this is the way it's happening. And okay, let me show some more example about it. We said reaction is regioselective. Why? Is because it's preferring a carbon with less substituent. Carbon with less substituent, and it's the opposite of the Markovnikov, regioselectivity. And the second thing, addition is happening to one side, because it's one side, we say is a stereospecific. Okay, either from the top or bottom of the molecule. And here we have an example. Okay, and as you see, we can add. This is an E isomer. In addition, it can happen. Okay, from the top or bottom of the molecule. If we add them to the top of molecule, we will have here the one with more substituent, it will get hydrogen, and the one with less substituent, it will get OH. Remember, we have hydrogen here, so I'm going to say there is hydrogen there. There is hydrogen there. Okay, and the carbon with less substituent got H. Now, the addition, it can happen from the bottom of the molecule. In that case, OH will be pointing down, and hydrogen as well. And of course, we have, forgive me, we have hydrogen here. Okay, so if you want to show it, like a 3D version of it, it will be like this. Okay, and then this one. Okay, hydrogen, it will be facing to us, and this bond again is facing to us, and what else? That one as well, it will be facing to us, and carbon, a hydrogen bond is facing to us, and now the methyls, the bonds that they are back, those I'm going to show them by dash line. That's CH3, and this one is ethyl. Okay, same story here. Okay, I got dash line there, and this one will be dash. This is going to be CH3. Okay, and so as you see, okay, I got some in the stereo centers, and if I assigned in configuration for them, for this one is going to be 1, 2. Okay, let's see, 1, 2, 3. This is going to be R configuration, and here, okay, see, this is going to be 1, 2. Okay, 1, 2, 3. This is going to be S configuration. Okay, and here, let's see, hydrogen is facing to us. Okay, I go 1, 2, 3. This is supposed to be R. It will be S. And how about here? Okay, this one is going to be 1, 2, 3. This one it will be R. So these two are enantiomers. Okay, so we got enantiomers. We can go on S turn to R and R turn to S configuration. Okay, last part that I want to actually talk about it. Okay, I have two isomers. One is E, the second is Z isomer, and these two are diastereomers. Okay, question is, are we gonna get a product that their relationship will be still diastereomer? Okay, and let's go after those product. Okay, so if we start with E, okay, the product that we get, if the addition, let's say the addition happened to the top, from the top we get OH there, and we get here H, so we will have hydrogen here, and forgive me, I'm gonna get hydrogen there. This is going to be hydrogen facing to us, and of course that one, this one will be back of the molecule. Okay, then that's going to be a CH3. Okay, and how about here? This one will go back of the molecule, and this is CH3. Okay, let's assign the configuration for them, and I forgot to draw this one. Okay, so and this one is facing to us. Okay, so OH and H up, and I have two substituents facing to up and to us and two back. Okay, the first first one is going to be 1, 2, 3. Okay, this is supposed to be R, S. It will be R. Okay, so again, let's double check. 1, 2. Okay, if we look at from the back of the molecule, this is going to be R configuration, correct? And how about this? This is going to be, okay, I go 1, 2, 3. Okay, so I have one here. Okay, 1, 2. This is going to be S configuration, and of course I'm going to get the enantiomer of it, so I'm not going to redraw that one. It will be added to the bottom. So I got S and R configuration. If I start with E and plus the enantiomer of it, and enantiomer of it, it will be R and S configuration. So S and R and R and S. Now, if we start with Z isomer, okay, what do we get? Let's add the OH here, and H is going to be added there. Okay, of course, this carbon, this methyl, it will be facing to us. Okay, so let's show this methyl facing to us. We will have hydrogen facing to us here, and this bond will go back, and that one as well. Okay, so I'm going to show them by dash line. That's going to be CH3, and that's going to be the ethyl. Okay, let's assign the configuration. Okay, so what do we have here? We have H, and this one is CH3. Okay, the configuration here we're going to get, let's see, this is going to be S configuration, or 1, 2, 3. This is going to be R configuration. So we got R configuration here, and how about this one? This one, if I look from here, this is going to be 1, 2. This is going to be R configuration. Okay, so I got R configuration, and enantiomer of this. Okay, enantiomer of it plus the enantiomer. Enantiomer is going to be S and S. Okay, so look, if we start with E, we get SR or RS. Okay, but if we start with Z, we get RR and SS. Now I want to know what's the relationship between them. Okay, the relationship between them. Okay, look, one of this got mirrored. Well, the second stereo center stayed as it is, like is R state R. If you don't mirror one of the stereo center, in that case, I'm gonna say you're dealing with like diastereomers. Okay, in diastereomers, one of the stereo center does not change. Look, this is 2s, and here this is 3R. Okay, and got to flip to what? To 3s. Okay, so one of them got mirrored while the second stayed as it is. And if that's the case, we say you are dealing with a diastereomer. So the starting point was diastereomer, got you a product that they are still a diastereomer. And this is going to be the end of this lecture. Thank you.